as opposed to the cost of an optimal path. And then for every single state, it also has a second variable, which is called the heuristic function. The heuristic function is an estimate of the remaining cost from that state to the goal. So for state S, it's the cost of that best path to get from S to the goal. And it also needs to be an underestimate, meaning that it should not overestimate the cost of the actual path from SS to the goal. Now, it turns out that in many kind of planning problems, you can compute that estimate rather easily. So, for example, in a 2D planning problem that I shown earlier, where you put a grid and you're searching for a path in that grid, a super popular heuristic function in robotics is a Euclidean distance, where it just estimates the straight line distance from any state to the goal, and that is a heuristic function. Of course, it's an underestimate on the cost of an actual path to the goal because it doesn't take into account obstacles. It also does not take into account the fact that on that grid we're only allowed to move, let's say, in 8 directions. So, you know, some other grids we could move in 4 directions, or sometimes in 24 directions, whatever. But it's we're not allowed to move in actual under any angle, and once again we're also not accounting for obstacles. So as such, that Euclidean distance heuristic function is clearly an underestimate on the cost of an actual path from a state to the goal, from any state to the goal. So once you have those heuristics, and those typically, it's important to have heuristic functions that it can be done very fast, that can be computed very fast. You can run the search itself, and A-star search has a very kind of a simple condensed pseudocode that I will show here. You start out with by initializing the g-values of all the states. So at the start state, the g-value is 0 because you know what is the cost of a shortest path from the start state to itself, and of course it has a value of 0. And then for every other state at the beginning, you have a g-value equal to infinity, which means that you don't have yet any path to any one of those states. So the cost of any path to any one of those states found so far is infinite. And then the search itself proceeds by what's called expanding states. It expands all the states in the order of their F value. So it maintains what's called open list, which are the candidates, set of candidates, states for expansion. Initially, that open list contains only the start state, and then as we expand state, it will put in more states into the open list. And at any point of time from the open list, it selects a state that has the smallest F value, which is nothing but the addition of the G value plus the H value. So effectively, the F value corresponds to an estimate of a least cost path from the start to the goal via that state S, because it consists of a G value, which is the cost of a path found so far, plus the H value, which is an estimate of the remaining cost of the path. So it expands, it selects a state that has the smallest F value from the open list, and it expands that. What I mean by expansion? Well, okay, before I do that, one property that it has is that every time it expands a state, it turns out that we can guarantee that the G value of that cost is provably optimal. So meaning that anytime it selects a state for expansion, it knows that it found the optimal least cost path to it from the start. Expansion itself is the following 5 lines of code, which number 1, it says that the state that was expanded is now closed, meaning that we know for sure that we have computed the state, we have an optimal path to it, we don't need to do anything else with that state. And then for every single successor of that state, we're going to see if its G value can be decreased. If we're looking at any successor, like the successor S prime, we're going to see what is its current G value, what is the current cost of a best path it found so far, versus the cost of a best path through that state S that we're expanding. So the G value is the cost to get to that state S plus the cost of a transition from S to S prime. And if we can decrease it, then that's exactly what we do. So we set the cost, we set the G value of that successor S prime to the cost of a newly found path, if it is better. And once we do that, we also put that state S prime, the one that whose G value we just updated, into the open list as a candidate for the expansion. So let me kind of, and that's the full algorithm. And as I said before, we do that until we expand the goal state, at which point the algorithm is done, because it will have an optimal G value of the goal state. So let me just kind of run this on the graph that we have in front of us. So as I said, we're starting out with the start state. That will be the only state at the beginning in the open list. So as such, that's the only state that gets expanded. As we expand that state, we look at all the successors. There is only one successor, namely state S2. And its G value is infinity. And of course, that infinity is larger than the G value of the start state, which is 0 plus the cost of transition 1. So which means that we're going to update that successor S2 by setting its G value to 0 plus 1, which is 1. And we're going to put that state S2 into the open list. So start state has been closed. State S2 now is sitting in the open list. Now, because it's the only state in the open list, that of course is the next state to expand. So we expand that state. As we expand that state, there will be two successors, state S1 and S4. They both have G values of infinity, and therefore both of those G values will be updated, and both of them will be inserted into the open list. So the state S1 is going to have a G value equal to 1 plus 2, which is 3. That, of course, is the estimate of the best path found so far from the start to S1. And the state S4 is going to have the G value of equal to 1 plus 1, which is 2. So they both get their G values updated. They both get inserted into the open list. Now we have two states in the open list. Now, of course, we're going to have a dilemma as to which state to expand next. We always select the state with the smaller G plus H. So the state S1 is going to have 3 plus 1. The state S4 is going to have 2 plus 2. So they both have the same summation, which is 4. Therefore, it doesn't really matter which one we select. So the ties can be broken at random. There are also ways to ties to break ties more efficiently, but algorithmically it doesn't matter in terms of the properties. So let's say we expand the state S1. As we expand state S1, we will of course update the G values of the successors. In particular, the successor is the goal state. So its G value is equal to infinity, which is of course is larger than 3 plus 2, which is 5. So we update the G value of the goal state at the expansion of S1, and that state gets inserted into the open list. Now, theoretically, at this point, we already have a path to the goal state. However, it's not yet guaranteed, provably guaranteed to be an optimal path until we expand it. And according to our rule, we need to be expanding in the order of the F value, G plus H. And of course, if you look at both of those states sitting in the open list, S4 and S-goal has a G plus H, which is 5, whereas the S4 has G plus H, which is 4. So state S4 is going to get expanded next. As we expand state S4, we update its successor, state S3. It now has a G value of 5. 5 plus 1 is 6, whereas the goal state has F value of 5 plus 0, which is 5. So the next state will be goal state. We expand the goal state, and at this point we're done. So the algorithm terminates, and we can utilize the G values that we have to reconstruct the path. In particular, the properties that we have are the following. So as I said before, every single state that was expanded is guaranteed to have G value to be optimal. So in other words, we're guaranteed for every single expanded state to have found an optimal course, the optimal path from the start to that state. For every other state that we have, the G value is an upper bound on the actual G value of that state, and we can, as such, we can reconstruct, we can use that backtracking that I explained earlier to reconstruct the least cost path from the start to the goal. And particularly in this one, it will be the path from the top. So here, while in this kind of a very small graph, we avoided the expansion of only a single state. In reality, of course, in a larger graphs, A-star search can avoid expansion of many states. So the properties of A-star search are that it's guaranteed to return a least cost path, and it also, the other property that it has, a very nice property, is that it actually guarantees that it performs a minimal amount of work required to find a provably optimal solution. So if you're measuring the amount of work that the search does in terms of the state expansions, then it can be shown that no algorithm can perform a smaller number of expansions than A-star search, given an arbitrary graph and a heuristic that goes with that. So it's kind of the best you can hope for. However, the heuristic function that we give the search to guide it has a huge effect on the performance of the search. So let's kind of look at the simplest example of 2D planning problem, where you have an obstacle that gives us this cul-de-sac, the local minimum. And let's see what happens if the search has zero heuristic, so no heuristic whatsoever, or the way to think about it, a heuristic function that is zero everywhere for every single state, versus, you'll see in a second, A star that does have a heuristic function that is non-zero. So if you have a zero heuristic function, the search starts out by expanding states from the start, and it expands them, continues to expand them in all the directions until it expands the goal state. So kind of graphically, you get this circle that encompasses all the states that were expanded, and kind of more theoretically can be shown that every single state whose cost of path to it is less than or equal to the cost of a least cost path has been will be expanded. So it's kind of the radius of the circle is the cost of a least cost path found. And you can clearly see that it's done wasted a lot of work by expanding states that are behind it and so on, for example. Now, if we were to take the same search and equip it with the Euclidean distance heuristic, so that distance that estimates the straight line distance from any state to goal, then the amount of expansions would look something like that. So you can, and it's the same optimal path that gets found, but you can see that it's a small fraction of the states that have been expanded by a search that has a zero heuristic function. So it's a kind of shows a dramatic improvement on its performance. However, if we're talking about higher dimensional planning problems, like if we go back to thinking about not just 2D planning problem, but rather planning for aerial vehicle or planning for self-driving vehicle, where the state space is 4 or 5 dimensional, then filling in all this big ellipse corresponds to expanding a large number of states. We're talking about a kind of having that ellipse in a 4-dimensional state space, or if we're looking at manipulation domains like this full body planning that I've shown earlier, we're talking about a 12-dimensional 12-dimensional ellipse. So that takes a very large number of states to get expanded. So weighted A-star search is a variant of A-star search, which is super trivial. All it does, it takes the heuristic function that you have and inflates them by a constant W that is supposed to be larger than 1. If it's exactly equal to 1, then it's a star search, but if it's larger than 1, then it's called a weighted A star search. As such, it allows you to trade off optimality for speed. In particular, the property, kind of a nice theoretical property that you have, is that the cost of a solution it finds is guaranteed to be no more than W, which is that inflation factor, by the cost of an optimal solution. It has also been shown that if you restrict the search to expand each state no more than once, then you get the exact same complexity as a star search, but you typically get solutions dramatically faster. So let me just kind of use a weighted A star search on this graphical example using the exact same Euclidean distance heuristic function and see what happens. So for sufficiently large W's, what it does, it shoots straight to the goal, then it hits a local minimum, and then it fills in this local minimum. So in other words, it expands all the states within the local minimum to find a path out of it, and then as soon as it finds the path out of that local minimum, it once again shoots straight towards the goal. So it does not expand any extra states that are not needed unless it hits a local minimum, in which case it needs to fill in the local minimum to understand how to get out of it. So that typically is dramatically faster than A star. So A star is dramatically faster than planning with zero heuristic, and weighted A star search is typically dramatically faster than A star search. Now, of course, you still need to fill in those local minima. And in high-dimensional robotic systems, those local minima, if we're looking at filling in a local minima in a 12-dimensional state space, you know, for any sort of a substantial local minimum, that could still be a lot of states. But now the shift from trying to kind of think about how to construct a graph or thinking about how to devise a new search algorithm shifted to the question of how do you design a heuristic function that has a shell local minimum? So if you can kind of have a system, robotic systems that you can analyze and come up with a heuristic function that provides you with a shell local minimum, then you're pretty much guaranteed that you will be able to plan online using weighted A star search with kind of a real-time performance guarantees. One of the kind of insights that I want to make sure that gets conveyed is that such a heuristic function can often be computed via low-dimensional search. So you can take a planning problem, you can think about it, how to identify a low-dimensional version of it, solve it, and the solution to it gives you that heuristic function that can be used to guide the full-dimensional search well. So particularly, you know, Euclidean distance heuristic function that I used as an example is actually not a good heuristic function for any sort of a complex robotic system. It's a very trivial heuristic function to compute, but it also does not give you a good guidance. It will not give you those guidance that will have a small local minimum. So if we look at the planning for self-driving vehicle, in a, let's say, 4-dimensional space, x, y orientation of the vehicle and a velocity. If you look at a Euclidean distance, then let's say you have a state in blue here, that's the start state, and the goal state is on the left. If you use Euclidean distance, then it will obviously disregard any obstacles that you have, and as such, it will give you a very deep local minimum for this 4-dimensional search. So it turns out that kind of one nice heuristic function, much nicer heuristic function that you can do, is a heuristic function that corresponds to solving a 2D planning problem. So if you take this domain, and by the way, in the red are the obstacles. If you take this domain and you do a two-dimensional search over it from the goal backward, then for every single cell, for every single state in this 2D, you will have computed a distance to the goal that takes into account the obstacles, and use that as a heuristic function. Then it will guide the search in a much better way, because it will automatically guide the search that, hey, look, there is an obstacle in front of you, so the path around it is the way to go, and that heuristic function will provide you that guidance dramatically better than Euclidean distance heuristic function. This is indeed the case that was, this is the type of a heuristic function that was used in the urban challenge that was mentioned earlier. So here is running during the race itself. The plan in red is the plan that's being computed and recomputed. It gets computed every 100 milliseconds. And it's in x, y, theta, and velocity. It's utilizing the lattice-based graph representation to generate the graph, and it uses that heuristic function, 2D heuristic function that I just explained, to guide the search. It also uses an incremental version of a weighted A-star search. It actually uses anytime incremental graph search, but I'm not going to get into those details. You can think about it as that it effectively uses a weighted version of A-star search that is also incremental, meaning that as it plans from one episode to the next, it reuses the search efforts to make it faster. You know, but the point is that if we were to use this planner with Euclidean distance heuristics, it will never work as fast as it was able to work with a heuristic function that was based on solving simpler, lower dimensional planning problems, namely 2D planning problems here. Same thing for aerial vehicles. If we go plan for aerial vehicles like those, this aerial vehicle, indoor aerial vehicle, or the outdoor aerial vehicle. This is a KMAX helicopter, full-size helicopter flying autonomously. So both of them planning is done in X, Y, Z orientation and velocity. So it's a 5-dimensional planning problem, and as such, it's a rather expensive planning problem. And the planner needs to generate and regenerate the solution every I think in this case 500 milliseconds. So in response to obstacles, in response to any sort of sensory input, like this indoor aerial vehicle, as it goes around, it has onboard sensors. It senses the obstacles, it adds them to the map. This map is being utilized for planning. Euclidean distance for both of those robots would not be a good heuristic function. Whereas if you do compute a heuristic function by solving a 3D planning problem, X, Y, Z, that gives you a much, much better heuristic function. So here, at every single frame, at every single 500 milliseconds, it runs a 3D search to compute a heuristic function, and then the result of that search, the values of all the heuristics are being fed into the full dimensional planner that searches in this 5-dimensional space, and of course the search and the graph generation are being interleaved. Finally, in manipulation, let's say you're planning for 7-dimensional arms like this one to pick up things over conveyor. So you need to be generating a solution fast. The Euclidean distance heuristics, once again, would not be a good heuristic function. Whereas if you utilize a heuristic function that was computed by solving a lower dimensional planning problem, namely a 3D planning problem, then that gives you a much, much better guidance to the search. and in particular gives you real-time performance, despite the fact that it's a full search is done in 7 dimensions. All right, now let's go back to the 12D full body planning. So if we look at this planning problem, where we effectively, let's say our goal is to have this object, you know, that picture being placed on the table, in the room, in the lab. So it's a high-dimensional planning problem. If we take kind of the same insight that we've just gone over and say, okay, well, why don't we compute the heuristic by solving a low-dimensional planning problem, particularly a 2D planning problem, to compute a distance to the goal location while accounting for obstacles. So in this kind of in the one heat map shown in the middle, that's the one that has is showing that the result of the heuristic function, where for every single cell, if it's blue, dark blue, that means it's very close to the goal. If it's red, that means it's it has a much higher distance to the goal. So if we were to compute this heuristic function, of course it's very fast to compute heuristic function, and then provide it to that 12-dimensional search, then what we're going to see, that movie that's being played here shows all the states that get expanded by the search. So it's not the plan that was generated, it's just the states that were expanded. And let me play it again. In particular, it actually shows a subsample of the states that were expanded. Show that. So initially, the search progresses very well. It expands all those states, progressing in the direction of the goal. But then it gets stuck in this large local minimum, where it tries to figure out how to reorient the arm to move through the doorway, whereas the heuristic function itself just guides the base towards the goal. So it has zero guidance about the fact that you need to position the arm, position the arms in a way that has that picture vertically. And of course, that gives you that deep local minimum where the search needs to figure out, expands all the states in this high-dimensional 12-dimensional state space to figure out that the picture has to be positioned vertically. Now, you can say, why don't we have other heuristic functions? In particular, one heuristic function that seems to be pretty useful is the summation of the base distance, so that 2D distance, plus the orientation of the object with respect to the goal. So the goal, once it hits the table, it needs to be horizontal. So the angle, the difference that you have, can be added yet another kind of measure of the distance from the goal. And that gives you a heuristic function that might be useful in terms of reaching the goal itself as you get closer to the table, but has no guidance in terms of how to proceed through the narrow openings where you actually have to reorient it vertically. So this once again shows the expansions of the search, and it pretty much gets stuck right at the very beginning because it needs to reorient the picture a bit so that it's kind of vertically, but the heuristic doesn't provide any guidance. In fact, the heuristic tries to maintain at the same orientation as at the goal. You can also come up with another heuristic function, which is the summation of the base distance plus the difference with respect to this picture with respect to being vertically. So that has nothing to do with the goal. However, it gives you that domain knowledge that if you want to move through the narrow passageways, then you do want to have that picture vertically, and that will allow you to kind of squeeze through the narrow passageways much better. So if we have that heuristic, then that goes through that narrow passageway very nicely, and it gets you to the table. But of course, at the table, it needs to reorient the picture horizontally, and that heuristic has no information whatsoever about guidance to make it horizontally. So the top one has exactly the guidance how to make the search put it horizontally, whereas the bottom heuristic function provides the guidance how to move the picture vertically as well as get close to the goal. Both of those heuristic functions are inadmissible. They do not underestimate the cost to get to the goal. They kind of allow you to have this domain knowledge provided, but they don't have that strict guarantee that they underestimate the actual cost to the goal. But you can see that at least the bottom heuristic functions actually can get pretty effective. It doesn't solve the problem, but it's pretty effective. So more generally, turns out that when you're planning for complex robotic systems, you can often decompose it into kind of a number of lower dimensional planning problems, and you can solve each one of them, and that gives you a number of different heuristic functions. So let's imagine there are n ways how you can decompose the planning problem, so you can get n heuristic functions. Those heuristic functions are not necessarily admissible, so they don't necessarily underestimate the cost to the goal. They could be arbitrary, but they could be still effective. So the kind of you can think about it that you can have n ways to decompose the planning problem. You can have n ways to relax the constraints you have. You could also have a perhaps a learning algorithm that learns some of those heuristic functions, and that gives you one or multiple ways to get those heuristic functions as well. So the question then is, can we utilize n heuristic functions, n of those inadmissible heuristic functions, simultaneously to make the entire search more effective, while at the same time providing guarantees on the completeness and the boundaries of optimality, just like the type of guarantees that we have seen in weighted A-star search. And this brings us to more recently developed algorithm that we developed in the group called the multi-heuristic A-star, MHA-star. So the idea, I'm going to explain it kind of through a few versions, starting with a very, very simple version at the beginning. So if you have n inadmissible heuristics, what you can do is you can run n independent weighted A-star searches and just hope that one of them reaches the goal. So this is the simple pseudocode for that, right? So you are effectively doing the round robin where you're iterating through all the heuristic functions, through all of those weighted A-star searches, and for each one of them, you're selecting a state with the smallest f value, where you're utilizing a weighted heuristic, so inflated heuristic, and they're just completely independent searches, and hopefully one of them gets you to the goal, and whichever gets you to the goal fastest, that's the solution that you grab. Now, in that simple version of multi-heuristic A-star search, you have a few problems. Number one is that just as shown in the previous example, you could have a situation where none of those searches actually get all the way to the goal and solve the problem, but each one of them has its own local minimum, and they just get stuck in it. The second problem is that you actually have n times more work than your regular weighted A-star search. So in a weighted A-star search, you can show that each state gets expanded no more than once. If you have n of those searches, then the guarantee you're going to have is no state is going to be expanded more than n times. And then finally, kind of the worst thing is that you also don't have any guarantees on the completeness. You also don't have any guarantees on the boundaries of optimality of a solution. So the first idea that is being deployed to make it more effective is that we can share information between those independent searchers. So if you have those n independent searchers and each one of them expands a state, then you can think about it that whenever it expands a state, it found a path to it, and then it propagates that path to all of its successors. So whenever we're looking at all its successors and we're putting them into the open list, those states are going to get inserted into the open list of all the other searches as well. So we're just going to have the successors being generated and inserted into the open list for every single search that we have here. With that, so this is the pseudocode for it. With that, it immediately gives us ability to have a synergy between those n weighted searchers. So we have kind of ability for them to collaborate and help each other to circumvent the local minimum, minima. So if they have very different local minima, one gets stuck here or the other one gets stuck there, then whenever one gets stuck, the other search helps you to get out of that local minimum, and when this second search gets stuck, then the first search gets help the second search to get out of local minimum. Also, we can use the same closed list across all the searches to make sure that no state gets expanded more than once. Meaning that if one search expanded a state, there is no point why any other search needs to re-expand the same state. It just doesn't give you any value. It was already expanded. We already found a path to it. There's no point why any other search needs to re-expand it again. Which immediately means that complexity-wise, we have a guarantee that all states are going to be expanded at most once across all the searches. So instead of n expansions, we can restrict all expansions to just one per state. So that cuts down on our complexity problem as well. Now, the only issue that we still have is that we still cannot provide a guarantee on completeness or bounds on the quality of the solution, because we are running n searches, and each one of them has a completely arbitrary inadmissible heuristic function. So you have n inadmissible heuristic functions. So it turns out that to resolve the last problem, we can kind of introduce one more search, what we call an anchor search, that assumes that you do have access to at least one admissible heuristic function. So it could be, heuristic function that was derived by solving some low-dimensional planning problem, like in this 12-dimensional space, solving this 2D planning problem for the base. You could theoretically, if there is nothing else, you could also use Euclidean distance, but whatever. So there is access to one admissible heuristic function. The heuristic function actually underestimates the cost to goal. And with that, you introduce that search, anchor search, that also expands states according to weighted A* search schedule, but it expands the states using the admissible heuristic function. However, that anchor search is only being invoked when necessary, and I'll show you that condition for when to make expansions out of the anchor search in a second. Now, if we do it in that manner, then it turns out that the algorithm is complete, meaning that it provides guarantees on being able to find a solution if one exists, and it also provides a strict bounds on the solution quality. So the rule for when to expand out of the anchor search as opposed to run those inadmissible searches, so the weighted A* searches using inadmissible heuristic, is very simple. Whenever the minimum priority, so the minimum F value in the open list of weighted A* search using inadmissible heuristic is less or equal than parameter W, which is our suboptimality parameter, times the minimum priority in the anchor search, if this condition is satisfied, then it's okay to proceed and expand the state out of the inadmissible search, out of the weighted star search that uses inadmissible heuristic. If, however, this condition is not satisfied, so it's larger, strictly larger, then we have to expand at least one state from the anchor search. And as you do expand the states from the anchor search, that will push up, it will increase the priorities, the minimum priority in the open list of that anchor search. And as you expand more and more states, this condition is guaranteed to become true at some point, and then you're going to switch back to expanding states from using inadmissible heuristics. So that's kind of a simple rule, and it turns out that you can show that the algorithm is complete, and the cost of the solution that is being returned by the algorithm is no more than W2, which is this W that is being used in this rule, times W, which is the inflation of those heuristics that we use in a weighted star search, times the optimal solution cost. So it's bounded by W2 times W. And also, you can show that each state is expanded at most twice. Once using n of those searches that utilize inadmissible heuristic function, and at most once by the anchor search. So if you have n searches, n heuristic functions, plus one more admissible heuristic function used by anchor search, then across all of those n plus 1 searches, you are guaranteed to have each state expanded no more than twice. So if we go back to this 12-dimensional planning problem, then I'm going to show the path that is being returned by the search, and you'll see in different colors. So the first portion of the path was found by the first weighted star search, the second one, the second, and the yellow one, that's the last one. Let me play that again. So you'll see those different colors, and the first portion, which is I think was the blue one, was found by the using the heuristic that corresponds to just the 2D 2D heuristic function, so xy of the base. The second portion, I think, was returned. Oh no! So the first one was a 2D plus the distance with respect to the vertical. The second portion was found just 2D heuristic, and the third portion, the yellow thing portion, was found using a heuristic function that corresponds to the 2D distance plus the difference with the goal orientation. So, and here's that's this thing running on a real robot. Once again, it all shows the solution, and kind of it runs this last version of multi-heuristic star search, and of course, even though it finds different portion of the solution using different weighted star search, the algorithm itself does it automatically, so it figures out automatically which heuristic to use when. All right, so the key points that I want to kind of make sure that I come across in this talk are the following. Number one is if you are planning for high-dimensional robotic systems, or for that matter, even if it is a somewhat low-dimensional, but not like 2D, but let's say a 4-dimensional system, it's very important to think about what is a good heuristic function to utilize to guide the search. And using a heuristic function that are just Euclidean distances and so on, those are often highly uninformative. They don't guide the search well, and it's very often beneficial to think about it. Can you come up with a lower dimensional version of that planning problem, solve it, and then the solution for it utilized as a heuristic function? And hopefully, kind of the examples that I gave are convincing enough that it can often be very beneficial. Also, if you kind of have more than one way to decompose the planning problem to low-dimensional planning problems, then there is an immediate question of, well, I mean, how do you utilize those multiple lower-dimensional planning problems? And multi-heuristic A-star search is a good way to utilize it. Weighted A-star search is just a utilization of a single heuristic function, whereas multi-heuristic A-star search is the utilization of multiple of them in kind of a simultaneously. Now, for those of you who may know, there are also ways to combine multiple heuristic functions into a single one by taking the maximum across them and so on. I haven't talked about it in this talk, but in general, while it's a kind of one way to utilize multiple heuristic function, it typically does not allow you to deal with this multiple local minimums, because if you are taking multiple heuristic function and combining them into a single one, then you are effectively preserving a lot of those local minima, and the search tends to get stuck anyway. So if you have multiple heuristic functions, it's very often it's way much more effective to utilize them simultaneously, just like was shown here in this talk. Now I will, for the next kind of 2 slides, I'll just talk about some of the directions in terms of going forward with the search-based planning and kind of my own interests related to it. So one thing that I find pretty interesting is to think about how to combine planning and learning. So you can do things like learn a heuristic function, in particular learn those n different heuristic functions and utilize it within planning. So that goes towards learning to plan faster from experience, from offline computations, and as well as demonstrations. You can use demonstrations to derive heuristic functions. There are also kind of aspects that are interesting in terms of interleaving planning and execution, and particularly how can we utilize experience to be able to generate more robust plans. How do we learn to plan from offline computations, kind of mixed with some of the human demonstrations. And one kind of item that we've been looking in the lab quite a bit is how do you plan with the imperfect a priori model. So typically the search-based planning is a version of a model-based planning where you rely on the model heavily to generate a plan. And of course, if the model is incorrect, then it's a problem. So here is this movie where we plan for manipulation and we assume that the object is light, but then when it tries to pick it up and tries to move it over the obstacle, it turns out that it violates the torque limits of the robot. All right. Now, how do you have a planner that adapts its behavior to compensate for incorrect prime models? And there are some interesting kind of question there. How do you combine learning and planning together? And how do you do it in a very much goal-oriented fashion so that it achieves the task? It doesn't have a goal of trying to learn the model correctly, because that may take a lot and lots of samples. But if you want to have a planner that achieves the tasks in real time, and that's kind of all it does is just tries to achieve a task, how does it do it when the model is still incorrect? And it turns out that there are some interesting kind of insights could be we could have to have a planner that has an adaptive behavior. The other interesting question, at least for me, is how do we have a robot that can generate plans that have kind of heavy interaction with the world. And in doing that, you kind of can no longer rely on a pre-encoded model. Particularly if you think about it, you know, in manipulation, when you're trying to, let's say, to grab an object and you know, push through the clutter, you cannot have a pre-encoded model that that a programmer encodes that shows how interaction happens with every single object in the scene. It's just too complex to encode it. And now, having said that, simulation tools have been utilized for decades, and those often do provide a much better fidelity models, and you can kind of use those inside the planner to instantiate the environment and simulate how it will behave as the robot interacts with it. Now, of course, the downsides of those are several. Number one is it's computationally very, very expensive to utilize it in planning. So if you have some sort of an analytical model, then generating a successor could take microseconds. If you have a simulator as a model to generate a successor of an action, then we're looking at easily half a second. So the question then is, how do you have algorithms that automatically reason when to utilize a simulator, when not to utilize a simulator, how to be strategic about what to learn offline to provide a better estimate of the outcome of action for online planning and so on. And then, of course, there is another, you still have a problem of closing the gap between the simulator and the real world, and that gets us back to the question of what happens if your model is incorrect. So anyway, kind of that's another thing that interesting to me is how do we devise algorithms, planning algorithms that are capable of utilizing simulation-based models effectively. So with that, I will stop here and see if there are any questions. And of course, I would like to thank students in my lab who have contributed immensely to this talk. With that, I'll stop here, see if there are any questions. And hopefully you could hear the talk all right.
Thank you, Maxim. It is really cool to see the work, which actually is the core of the modern driverless car technologies. Yes, so this DARPA challenge is the event which actually starts all this hype with driverless cars and so on. And it's really cool to see the researchers who participated in that. So, questions, please.
Sure, thank you. Yeah.
Thank you for your talk. It was really interesting. I have several questions. The first one, all the cases that you've shown were with static obstacles. And can these high-dimensional planning methods be used with dynamic obstacles, or they may occur some problems? It's the first question.
Yeah, no. So first of all, I guess a little bit of clarifier on what we mean by dynamic obstacles. So the word dynamic sometimes used kind of in two meanings. Number one is a case where your environment may not be known in advance, and as the robot proceeds, it learns the kind of the actual environment, where the obstacles are and so on, and updates the map, and it has to replan. So it's not truly dynamic obstacles, it's just that the environment is not known. Of course, in these cases, this is a kind of a typical setup on real robotic systems, and even in the movies that I've shown, that is always the case, right? The aerial vehicles flying around, discovering obstacles and updating the map, and so on and so on. So and there, you have to be able to plan within 100 milliseconds and so on, primarily because you're updating the map and you have to respond to it. Now, if you mean by dynamic obstacle, truly dynamic obstacles, meaning that, let's say there is another vehicle that you have to go around and you have to plan knowing that that other vehicle is also moving, then in this case, it goes back to how you constructing graph. So it's very important to think about the construction of the graph. So in those cases, you have typically you would have a time as an additional dimension in the graph. So you would be, let's say, for the same self-driving vehicles driving on a highway or so, you don't just plan an x, y, theta velocity. You also have time as another dimension for every single dynamic obstacle that is being perceived by the vehicle. You have its time parameterized trajectory as an input, so you know kind of the prediction of how they're going to move, and the aim of the planner is to generate a trajectory that is collision free in space and time. But otherwise, it's a graph. And you can employ the same type of algorithms like weighted star search and so on that graph that now has a state that includes time as a dimension. Now, also, there have been some work, including from my own group, on searching through those graphs that include time as a dimension and kind of exploiting some of the kind of specifics of the time. Time is a peculiar dimension in the sense that it only goes forward, and you can utilize this in some special way. So the one example of that is what's called a safe interval path planning, where you can kind of utilize some of this insights to compress the planning, this graph representation pretty well. But in general, it's a graph. So and as such, you know, it's kind of can still be, you can still utilize weighted star search and so on to search for it. So I'm not sure. Does that answer your question? Is that kind of what
you have answered my question. Thank you.
Okay,
and another question: am I right that multi-heuristic search is not complete? It means that if there exists path, the planner may not find this path.
No, so if you're using multi-heuristic star search like that last version, which includes the anchor search, it is guaranteed to be complete. So it is absolutely complete. Yeah, it's complete, and furthermore, it bounded suboptimal, meaning that you can control how much of a suboptimality you allow. So if it's you know, you can set up your W2 and W so that the solution you get is guaranteed to be no more than whatever 2 times the optimal. So you have a control over that.
Okay, thank you.
Yeah.
Maxim, thank you for the talk. I have, I think, 2 questions. First of all, can we try to take search-bounded suboptimality approach and reducing high-dimensional problem to a lower-dimensional problem and apply it to sample-based approach? Does it make sense to you, and did you consider it? I mean, you're talking about search-based approach, and I think sample-based can be used too with this.
Yeah, right. Yeah, it's a good question. Yep. So so there have been some works, not from my lab, but from other labs. There have been some works on trying to use heuristic functions in the context of sampling-based planners. And you know, it has some success to it. Now, of course, philosophically, there is a little bit of a dilemma in there, in that sampling-based planners kind of try to explicitly perform this sparse exploration of the entire space. And because they do that sparse exploration of the entire space, they escape local minima pretty fast, right? So if you have a problem where there are no narrow passageways, but rather it's just large local minima and the ways to get to the goal are also pretty large, then by doing the sparse exploration, you can escape those local minima fast. You're basically doing a very sparse exploration of those local minima. Now, as soon as you have a heuristic function, you're saying that you should be driving the search in this particular direction, and that goes against this philosophy of a sparse exploration. So there is a bit of a dilemma in that the use of a heuristic function assumes that all you do is trying to guide the search, whereas the sampling-based planners, they do the opposite, which is they try to do the sparse exploration of the space.
But if
now,
we have multiple heuristics, then we can kind of...
Right, yeah, no, that's an excellent point. So to my knowledge, I have not seen yet that type of work. I think that's a very interesting that's a very interesting, would be very interesting to see that, which is utilize the multiple heuristic functions, multiple, in particular, if you once again go back and kind of look at the planning problem and decompose it into multiple lower dimensional planning problems to solve each one of them, and then have some way to incorporate those multiple solutions into the sampling-based plans. I think that can indeed be very powerful. I'm not aware of that work. My lab doesn't really work on a sampling-based planner, so it's certainly not from my lab, but I think that would be interesting.
And another question, thank you for the first one. And another question is, can we use multiple heuristics as like voters and just choose the next node to expand just from the voting from multiple heuristics? Is it kind of useful? Can it be useful?
Yeah. So it's an interesting question. We have experimented with, so it's not exactly voting, but we have experimented with putting on top of n of those searches. We have we put on top a learning algorithm, and particularly like a DTS, dynamic Thompson sampling algorithm, which effectively monitors the performance of each one of those heuristic functions, and whichever does the best so far, so it's kind of progresses towards the goal, that's the one that gets more and more resources to it. So it gets more and more expansions allocated to it. And then, but whenever it gets stuck, then it quickly has less resources to it, and some other search it gets more and more resources. So it actually very, very helpful indeed. So I'm not sure, whether that qualifies as a fully voting scheme or not, but intelligent managing of those searches as opposed to doing simple round robin is definitely helpful.
Thank you.
Yeah.
Hello, Maxim. Thank you so much for such interesting presentation. And I have the question concerning the beginning of your presentation when you said that first of all, we need to build the grid upon the map that we have. And can you elaborate, please, how you decide on the size of the cells in this grid? So, because if there will be too many, it will be very complex to solve this problem, and otherwise it will be too simple. So we can miss some good solutions.
Right. Yeah. No, that's a good question. So, and typically, you know, that this trying to think about what is the right discretization is an important aspect. And so it's like thinking about how to generate the graph in terms of dimensions to use and what are the actions, that's one thing, but then the discretization is on its own an important aspect. There are several answers to that. Number one is you typically have to think about the kind of what are the minimum narrow passageways that you expect to have in the environment. So, you know, given the size of the robot, what is the clearance you're going to have? So, for example, if you're talking about planning in a parking lot, then you have to think about it, okay, how close the robot is going to get, the vehicle is going to get to the other vehicles. That clearance, so let's say it has to get at most, let's say, 25 centimeters to the other vehicles, then that tells you that you want to have a discretization that is, you know, roughly half of that clearance, no more. Otherwise, you're going to be indeed blocking some of those solutions, and you'll not be able to generate a solution. You have to think about it, the size of this narrow passageways. You also have to think about at what resolution the perception data gives you its own information. You know, how big or small the obstacles can be. Now, you're absolutely right that if you're looking at very large environments, let's say for those aerial vehicles that are shown, you know, if you're looking at a planning over 10 by 10 kilometer area, yet there is a small portion where there is like a narrow passageway. For some reason, there you have to be operating in the space where you may have to get to within a meter to some to obstacles. Putting this fine grid, 1 meter grid over the entire 10 kilometer area could be overkill, and it quickly becomes computationally expensive. So if you do find yourself in that scenario, then very often you should be looking at what's called adaptive grid discretization, so where you basically have some cells that are large and some cells that are small, and in particular there are kind of ways to do that, including like a quadtrace and so on, which start out with the large cells and then split the cells that contain obstacles when kind of to smaller cells and so on. Now, the downside of those techniques, of course, is that it's much computationally more expensive to construct them, to maintain them, and so on. We actually have recently, from my lab, we've recently developed an algorithm called multi-resolution A-star, which is very similar to multi-heuristic A-star that you just seen. Multi-resolution A-star has multiple resolutions that it searches also in parallel to each other, and then shares the solution. And that gives you kind of a way where you can utilize the coarse resolution to find the spaces that don't have that narrow passageways, and then whenever you have a narrow passageways, then the fine resolution kicks in. So that's another way to do that. So, but in general, you're absolutely right. When you have a very large environment and at the same time you have a narrow passageways, then you have to think about what resolution to pick, and it could be non-trivial. You know, some of those techniques like multi-resolution and adaptive discretization helps with that. Does that answer your question?
Yes, thank you.
Mm-hmm.
I'm just speaking about the title of your paper. If you count the number of students, it's 12 students, so it could be called 12D.
12D.
Yeah,
I haven't
exactly. That you understand what I mean, because actually you have the just three-dimensional space, and just several processes goes in parallel, and that's all. it's not. If you will count this number of space, then you have the car and the wheels and the lights at with the car. So actually, should be more careful, because I'm interested especially in dimensions, and this is not play with dimensions. Just you have some maybe I'm wrong, so you will reply. But still, it looks like you have just separate pieces of the problem, and they solved one after another, and they connected to each other, of course. So have to take into account solving one problem with another, and so it's rather clear and understandable stuff, but shouldn't say that it's 12 dimensions, I think. Thank you.
So, yep. So the I think if I understand correctly, what the point is that not all dimensions are the same, in a sense that some of those dimensions are truly dimensions that can be looked at a large spectrum of values, and some of the other ones are actually small dimensions where only a few values are there. And as a result of that, it really is not necessarily about the dimensionality, but it's more about the overall size of the planning problem. So I think that sounds like, to me, one of the aspects of the question. And that is indeed absolutely correct in that there are some problems where, let's say, you have, I don't know, let's say 5-dimensional space, X, Y orientation and velocity, and then a gear, for example, whether it's whatever the gear that you're in. But then the gear that you're in is really only like 3 or 5 values. Now, at the end of the day, what really matters is the overall number of actual states that the vehicle could be in. And you know, the 12-dimensional state space that we're talking about, this PR2 robot, full-body PR2 robot, at the end of the day, it is a, you know, if you look at it, it's a 10 to the 19 states. So, you know, whether it's 12-dimensional, 10-dimensional, doesn't really matter. The point is that it's a very, very large state space. Now, if those dimensions were completely independent, then it would have been an easier problem indeed, because you could just solve it for the, let's say, for the base, plan for the base, and then you can solve it for the arms and plan for the arms. If you could decouple it that way, you're indeed looking at 2 separate planning problems, solve them separately and so on. However, in a lot of planning problems, even including this 12-dimensional space, it's the coordination between those multiple dimensions that makes the problem difficult. So as the robot moves through these narrow passageways, it has to utilize the arms to reorient this thing, and it has to move the base at the same time. So you have interaction between the XY theta of the base, and you have interaction with the degrees of freedom of the arm. For example, when planning for the same PR2, opening a door, it is once again a full body planning problem, because it requires the coordination of the base with the arms, and that makes it difficult. Now, of course, you know, there is things like a closed chain and so on that could be utilized to still kind of think about how to construct the graph more efficiently, but still, it is a coordination between those dimensions that makes it difficult, and you can no longer just decompose it into 2 planning problems and solve them separately. If you do that, you know, you typically run into that problem where, well, I mean, there are all those situations where you have not accounted for how those dimensions interact with each other, and then you get problems where the robot is getting stuck and you know, doesn't know how to proceed. Does that answer your question?
Okay,
Yeah,
thank you, Maxim.
I think
Unfortunately, we
there is
ran
no
out of
time.
time, so we have no time for the next questions. But
all
the
right.
discussion was, I think, really fruitful. Thank you again. It was a pleasure for us to see you here.
Absolutely. Yeah. If you guys have any more questions, just shoot me over email.
Sure.
Okay.
Bye.
All right. Thank you very much.
Goodbye.
Bye.